Thank you. Thank you very much. So you hear me well? Okay. So thank you for having me. I'm very honored, and it's as it the first time I'm invited to this time research forum. And so first of all, I wasn't sure about this audience. So I don't know if most of you are neuroscientists or you come from more psychology or neuroscience. So I try to be quite not bit broad and to be sure I'm understood by everyone. So I hope I will not bore some of you. Uh, okay, so I'm François Foster. I'm a postdoctoral fellow in France at the University Hospital of Strasbourg, and I'm part of the Anne Girsch lab. And so we work in psychiatry. So I'm doing cognitive neuroscience about and studying the temporal processing in different populations, healthy volunteers, but also psychiatric patients, especially schizophrenia patients. And now I'm going to talk about the recent work I've done with people that play video games and their ability to implicitly process time. So just trying to fix this bar. Okay. So um, animals and humans, we need to adapt constantly in this changing environment. And the best way, one of the best way to do it is to anticipate all our sensory signals in space, but also in time. So beyond the fight or flight situation of animals, us humans, we have these timing mechanisms that are very important in, for instance, artistic activity, dancing, music, that has been largely studied. Also in sport, of course, as some of you might have seen, like the Olympic Games, when the motor timing is very, very crucial to outperform to our task. And we were interested in our European Consortium of Research in Psychiatry about video games. So basically in many, many video games, as you can see here on the right side, you have this kind of very typical situation when basically, again, it's about motor timing. You perceive some information very quickly and you need to behave in a very specific way at the exact right timing. And because you have this exposure thousands and thousands of times in the population, the players that plays hours for every day for years and years, our hypothesis is that all this implicit learning of time intervals can be completely automatized. And so maybe the ability to implicitly process time is altered. So, so could video gameplay influence our implicit time processing? And this is very important for psychiatry because there's a new trend in the field that proposes actually video games could be one of the best tools we have for cognitive rehabilitation. And the idea is simply that video games are highly engaging. And so they could be a tool that actually, a solution that where patient could actually practice this. So what we want to do, some of us in psychiatry wants to do to design proper rehabilitation tool that are actually engaging people so they would actually use it. And so to study implicit timing, we use the VIAB4 task. So I think that some of you might know, as given the talk before. And so the simple idea of the VIAB4 task is that you have this arrow of time, you have a point t in time, your present moment, and you have the passage of time. And if you have to anticipate something in time, you will, for instance, anticipate something that close at the near future, time plus 1 and time plus 2. And if now you have sensory signal such as a visual cue like this, a red light, you will anticipate that the state of the world will change. So this red light will become green at some point. And so as time elapses, the chance for this light to change state, become green, increases. So this is reflected in the work we saw before, of course, the as a function. And we use this task, the VIAB4 task, to study implicit time processing. And so in the lab, we simplify these like before, with, for instance, two simple time intervals, time plus 1 and time plus 2, 400 milliseconds and 1 second. And so here, basically in this situation, you only have the passage of time that helps you to anticipate the stimulus in time. But there's another situation when you have explicit information that tells you they can guide your temporal expectations. So for instance, if before this signal, I tell you in 400 milliseconds, so time plus one, you have the target. In that case, when you have the signal, you will have temporal attention mechanisms that will allow you to know that 100% of the case, the stimulus will appear at that moment. So these are the targets, so I can prepare in a specific way my motor response. And so this temporal attention is important because it allows to mobilize our cognitive resources when is it required, so we can use better strategies to manipulate our resources. And from the data, we saw that, of course, that optimize our behaviors in the sense that our response are faster or more precise. Okay, so what we did, we use this task in people that play video games and controls, of course, and we use this task in virtual reality. So the point of using virtual reality, again, is because at the end of the day, what we want is a tool that could be used in clinical settings. So doing a task that is not just a classical experimental psychology task that can be quite boring sometimes, but finding some way that is very engaging for the participants. So not only for the participants that come back to the lab, but at the end, if we found some markers that are very interesting, we could actually use it in clinic. And so we have these people that went in the lab, they experiment in virtual reality, and the task is last presented here. So we have first a green light that tells us that the target will come at some point. It changes state, it becomes gray, and when it's gray, there is time plus one or time plus two, these two for period, these two time intervals. And then the target appears, the red light, and they have to press the button as fast as possible. So I have a video that shows that. I will just try to move slightly like this. I hope everyone will see it quite correctly because with internet, we never know. So people are in virtual reality. They have this controller in their right hand. They have the different robots. There's a green light. They look at it, turns gray. This is the waiting period. Then they have a target and they press it as fast as possible. So the idea of the experiment still is very basic, even though it's virtual reality, can be still unfortunately a bit boring. And so here, as you can see, there is two types of robots. They were giving contextual cues. They are colored and the gray robots. And the idea here is that in one case, people have to play with this gray robot. That's what we call the neutral cue condition. So people have no idea when the target will appear, either time plus one or time plus two. And in the other case, they play with this colored robot that plays the role of temporal attention. And they tell them in advance if the target will appear time plus one or time plus two. So in the first case, they have to anticipate in time the target only based on the passage of time, which is completely implicit because you don't have to think about time. It's highly automatic. And in the other case, you use a temporal cue, which is explicit. It's an explicit information. And so you have temporal attention mechanisms that will help you to anticipate and prepare your motor action. Okay. And so our population were the people that play video games, action video games to be precise. And these people are playing basically on a daily basis. Usually it's like more than 20 hours a week. So it's quite intense. And control population, a sample, of course. So people that don't play video games that we call the NVGPs, non-video game players. Okay. So the first thing we're interested, of course, is the reaction time, the behaviors. And so what we expect in these traditional variable paired task is this kind of patterns. So people would be faster to respond to the target at the second interval than the first one. Not only because they have more time to prepare the action, but also because at that moment, at the time interval, the T plus one, they are not sure 100% that the target will appear at that moment. Whereas here, 10 plus 2 is the final interval. They know 100% it will be the case. So what we're interested, of course, is this slope, the difference between these two periods. And this slope represents somehow this implicit benefits from the passage of time. How much people benefit from the passage of time. And what we're interested in this task, of course, is this slope. But I propose a specific calculation that is, for instance, that is called the gain in other psychophysical task. So we're interested not only in the difference in milliseconds, but for each participant, so independently of the average speed of response, what is the speed change? So how much faster people are here, time plus two, than compared to the situation in time plus 1. So it's very simple formula. We take a baseline condition, for instance, condition A here in green, minus condition B, we divide by condition A, and we multiply everything by 100, so to have a percentage. And if we change these variables with our values, so here in that situation, that person will be 20% faster at time plus 2 than time plus 1. So the benefit from the passage of time will be approximately 20%. That's interesting. The interest in that as well is that we reduce the variability between people, between participants. And so we apply this formula in gamers and non-gamers. And of course, in the case of the neutral queue, so it's only based on implicit processing of time. There's no attention. In the case, there is attention. So with the temporal queue. And here is what we found. So on the left side, you have the gamers. On the right side, you have the non-gamers. In black here, you have the benefit from the passage of time, this calculation in the neutral queue condition, and in red in temporal queue condition. And so what we found is basically a group difference on the neutral queue, such as gamers actually they benefit better from the passage of time compared to the controls. And this is only in the neutral queue condition, not in a temporal queue condition. So that goes in favor of our hypothesis that maybe they have better implicit temporal processing, these people that play video games on a daily basis. And we use the same formula to see if people, how much faster people would be using the queue. So we just replace these variables with here temporal condition versus neutral condition. And what we found is that basically everyone benefits from the temporal queue. That's why the values are mainly positive, but there's no difference in the groups. So people don't, these gamers don't benefit more than controls in using the temporal attention. So now from the data, we try to understand what are the mechanisms behind that, how can we explain that gamers play benefits better from this passage of time. And what we did is during this experiment under this virtual reality headset, people had wear an EEG. So we have EEG recording during these sessions. And the first thing we look at the CNV. So actually, I think most of you might know. And we didn't find group effects in these. So I skipped that part. And but what we looked at is also two different markers of temporal expectations, and we based our work from André Cravo and a paper has been published 10 years ago. So the first thing is the theta band recorded in frontal lobe. So in the paper, they suggest, they show that the adjustments in theta power contributes to a central mechanism for controlling neural acceptability according to temporal expectation. So when we expect in time a percept, a stimulus, your theta power will be modulated. So we looked first if we have this theta power in a task, and indeed, this is what you can see in red. So the red area is basically the increase of theta power during the waiting of the target. So we have indeed this oscillation present in our data. And then we looked at it in the two groups and in the two conditions. So in the neutral queue condition, these gray robots, here, basically you have the warning signal and the targets over here appear. And we're interested to compare analysis like with the original paper. So we looked at the data over here, which is time plus 1 when the target could have appeared but did not. So basically there was 50% chance to have the target over here. And here is the temporal queue condition. So it's similar, except that in advance, people know the target appears over here. So here, technically, they know there is 0% chance that the target appear. So it's either 50% chance or 100% or 0% chance. So looking at this data, we found two main effects. One main effect of the group, because gamers have lower theta power than controls, and the effect of the queue, such as in the neutral queue condition, the theta power is increased compared to the temporal queue condition. And so from these data, we draw two conclusions. The first is that this theta power is increased when the target probability occurrence is higher, which is here in the neutral queue condition, 50% chance. So that goes with the paper in the same direction, that there's a link between temporal expectation and mid-frontal theta power. And that helps us to understand what happens in gamers, because here in gamers, they have a decreased theta power in red, and it's possible they have decreased temporal expectation compared to controls when the probability of target occurrence is indeed low, because you see the 51 chance over 2 or 0%. So is it possible that they have better adaptation? The strategies to apply the temporal expectation might be better adapted in gamers. And so we follow up this analysis with another one as in the papers, that show that maybe it's related to specific neural communication strategies. So what we did is this phase power coupling in theta and beta band. So I will just try to explain clearly how this works. This is what we call the functional coupling in EEG. Imagine two types of oscillation. One that is very slow, like here in blue. This is, for instance, our theta power that we found in the mid-frontal area. And there's another oscillation that is faster, here in green, that we can find in the frontal cortex as well and in the left motor areas. And just to remember, in this task, participants answered with their right hands. So that's why probably we have a beta on the left motor area. And so the idea is that if we have a perfect coupling, so this is just an example, it means that when you have a specific phase value of this theta power, you have also a response of another oscillation in another part of the brain. And so here, for instance, every time the oscillation is a specific position, we have a response in other brain areas. So there is a functional coupling that is at work somehow. So we look at this coupling between this frontal and left motor area in the two conditions and in the two groups. And so what we found is here in gamers. So basically here, to be short and simple, the more yellow it is, more coupling there is. And if it's completely black, there is no coupling at all, which is almost impossible. And so what we found is that there is a stronger coupling in the neutral Q condition compared to the temporal Q condition in gamers. So when there's no attention, we have this coupling. And when we compare with controls, there were no difference. So maybe this functional coupling is involved indeed in the ability to implicitly process time. And so there might be a relationship between this coupling and these benefits from the passage of time that I proposed before from the reaction time data. And this is what we found indeed. So basically, the higher is the coupling, more people will benefit from the passage of time. This is what we see. And this is from the data in the neutral Q condition when you don't have attention. But when you have the temporal attention, also this coupling disappear. I mean, this relationship between the coupling and the benefit from the passage of time disappear. So maybe indeed gamers, they have a specific communication between different brain areas that can help them to better process time. All right. And the last point I wanted to talk about, I think I have, it's a bit tight on time, but I will be quick. Because now more and more labs try to create to set up virtual reality experiments for many different reasons. And for this experiment, we use virtual reality that is as embedded night tracker. So you can actually record the ocular movements during the task. And so this is very great for cognitive neuroscience and psychology. And so we're interested in one thing in particular. If I ask you to look at this red dot in the front of you, you will think that your gaze is completely stable, where actually it's not. If we look at the eye tracking data, we would find tiny saccades. That's what we call microsaccades, and we are not aware of these. What is interesting is that it has been found the last few years is that these microsaccades are basically inhibited by temporal attention. So when you know that a stimulus will appear, you will have the probability of doing one of these microsaccades will be lower, inhibited. So when we look at our data, here, this is the probability of doing a saccade over time. You have the first signal, then you wait, you have this response. And then here, you wait for the target that appears at that moment. And indeed, the probability of doing a saccade is way lower in the temporal Q condition. So when you know 100% of the time the target appears at that moment, than when you do not. And what we were interested here, however, concerning our gamers, is this response. So when you have to process this first signal that tells you, okay, you have to wait and anticipate for the target, you have the probability of doing this saccade is very particular. There is an inhibition and then a rebound. If you look at the data, recent data that has been collected with traditional eye tracking system, it's very similar. And the idea is that here, this response reflects somehow the processing of the stimulus, and it can be modulated, for instance, by attention. This was for this task from the paper cited. And so we looked at this response to the first stimulus in gamers and non-gamers. And what was striking is that basically the response is the same, except that it just occurs earlier in gamers. And to do so, we calculated the latency of this peak inhibition and the latency of this peak rebound, and both were shorter in gamers than non-gamers. So maybe this can explain as well why they benefit better from the passage of time and the relationship with their implicit time processing. And actually, what we found using another correlation is that people that benefit the most from the passage of time from the index we calculated are the people that have the shortest oculomotor response. Okay, so to wrap it up, because maybe I'm short on time, just a few take-home message. So from marketing reports published last year, we know that more than 70% of the population between 6 and 40 years old play video games, can be at home or in the public transport, anywhere. And the average rate is 7 hours a week. So it's huge and it's increasing. So we have a huge part of the population that practice these video games. So it's very important to understand what are the benefits and the costs of this practice. And especially if there is benefits, we need to take them and maybe it can influence what we can do with other people for cognitive enhancements and rehabilitate some patients, for instance. So from this data, we found that an enhanced implicit temporal processing in gamers. So maybe we could use these video games as a base to design intervention and program for rehabilitation with people that have deficits in temporal processing, such as schizophrenia or bipolar disorders. We found that action video games might shape some neural mechanisms that are involved in temporal cognition. We need to understand what are these. We have some ideas, but we need more research to replicate these results. And it seems like action video games can affect our oculomotor systems. Why and how is still very obscure. We don't know, but there might be a relationship between oculomotor response and temporal processing. And I will thank you for your attention. I thank you, my lab, the INSERM in Strasbourg, and thank you for your attention.
This was a good, interesting talk. So if anyone has any questions, please go ahead and raise your Zoom hand or type in the chat. Question, were the reaction times generally faster for gamers?
Okay, yeah, thank you, sorry. So indeed, they were slightly faster, not as much as expected, but they were slightly faster. But what was important is basically we had a lot of different variability in the two groups. A huge variability in the non-gamers, but in the gamers, they were all the same profile of reaction time. And so we had to face a problem of variability in the two groups. And that's why I came up with this speed change index. So somehow it completely reduced all the variability between people. I think he replies to the question. I see another question from Kevin. This temporal processing advantage in gamers is a few milliseconds. How much do you think this transfers to other abilities? How big is the effect in athletes? It seems crucial for the rest of us. How much of an impact does it have on cognitive abilities? So indeed, it was a few milliseconds, but that's why actually this index actually it's important because it's not just about a few milliseconds, but you have to think a few milliseconds compared to what is the basis. So here, indeed, it was not too much in this task. It was like between 5 and 10%. And how much it transferred to other abilities and how big is the effect? I don't know yet, really, because this is very new. So these data are like a few months old, and we started replicated this result and look at them in patients, for instance, in psychiatry. So I don't know much yet. And in athletes, indeed, it's crucial. And for the rest of us, I don't know, for the cognitive ability, maybe really depends on the task, really. So I would be interested to know how this happens with this index, for instance, in musicians or dancers or other athletes, indeed. But I don't know yet.
Thank you. And well, yeah, I mean, actually, I believe that probably has a big impact because we're having lots of little decisions all the time. And if all of these are improved by a few milliseconds, then a whole thought process might improve by, 100 milliseconds or something if each time it's a small bit. But I thought the question was interesting. So thank you very much.
Indeed, you're right. So it really depends. If you think that in a situation of multitasking, this can be very important indeed. But I have no idea. I don't study multitasking, but indeed, it's a very good idea. Actually, very good point. Thank you.
One last question, Kumar. Go ahead, please.
All right, two quick questions. Your talk was beautiful. I was wondering if the theta was locked to the Q and if you'd ever looked at errors.
Okay, so just to be sure about the errors, indeed, I didn't present them. And what we did the errors, so basically when people press the button before the target, these are the errors you're talking about, anticipation. And so, yeah, indeed, we look at this anticipation, and gamers, these people that play video games, do less errors. So we can think that about motor impulsivity. Actually, they're reduced compared to what people would think in the literature, saying that the games, playing games make you impulsive. Actually, we found the opposite. And so yeah, please.
I'll bet you that the errors trigger a prominent theta response that lasts. So it might be interesting to look at.
Indeed, I didn't look at the data. Actually, I get rid of this data because you have a motor response during the waiting. So it's a problem for EG analysis for clean data. But actually, this is another type of data that will be interesting to look at. There were very few, like 2 to 5% of the time, because fortunately, people did the task we asked them to do. So what are your thoughts on the application of this project on rehabilitation? So there's different things. And first of all, actually, I'm writing for, I'm trying to get a grant for a proper rehabilitation project here to do this really an intervention and see really if video games change this, create this effect, to be sure. And so the idea is really, if we know that, for instance, in at least in schizophrenia, there is disorders of implicit time processing, not explicit. So somehow there's research that shows that this implicit time processing could be related to the cerebellum. And so the idea of practicing something like video games, doesn't have to be video games, something like it, similar, that really train these mechanisms, somehow some patient could really benefit from it. But there's no data on that. No one did ever anything like this. And I hope the European Commission will give me the opportunity to show that if it does or not. And rehabilitation. So the thing is, they remind me that in my data, I don't know, but I know that the FDA in the US, they accepted a kind of video game like this when kids from 8 to 12, if I remember correctly, 8 to 12, they play these kind of specific video games for ADHD. And the paper has been published in the Lancet, and it's really great results. And so that's why now there is actually a lot of grant and research that is done to know if we can extend to other pathologies, psychopathologies. And that's why in my consortium, we're interested in schizophrenia, bipolar disorders, depression, autism, and yeah. So it's great avenues, I think. The idea of video games, we have to think that really the idea is not to use video games, but to inspire designers and programmers to design really tools that could be used for clinicians, which is something that for clinicians, it's another part of the world. But it could be very great and helpful for people.
And just one point about that, the control groups are important too. In that FDA approved video game, the control group was, I think, a puzzle solving game, which wasn't exactly the same kind of comparison. So I mean, it's great that it got that, but in general, in designing these, I would recommend to make very important, careful decisions about the control groups to improve the
absolutely
validity.
It's very true. Yeah, to be sure that it's actually the specific aspect of your activity is not just any activity that is close to just being stimulated. Because of course, if you compare that to just doing nothing, a lot of things that helps compared to doing nothing. All right.
Do you have another question or?
No, sorry, I'll take it
No
down.
worries. Of course. Okay. All right. Thank you so much, Francois and Ellison. These were really great talks.